Here's number 15 from the momentum review. A bullet is fired into a pendulum as shown in the picture on your review paper. Given that the bullet has a mass of 0.01 kilograms and the pendulum has a mass of 0.3 kilograms, we're going to find the maximum height, call that h, that the pendulum and bullet rise together, given that the initial speed of the bullet is 225 meters per second. This is an inelastic collision. The picture's not drawn here because it is drawn on your review paper. So the first things first, we're trying to find the maximum height of this pendulum. And this is a section that deals with momentum, and there's no height anywhere in momentum. It's all m's and v's. So how the heck do we do this? So first things first, I'm sort of going to work backwards to let you know my logic and how we did this. I need to find the height that this pendulum is going to go. Well, what section of physics dealt with pendulum motion? And that was the conservation of energy. So if I look at the conservation of energy, initially this pendulum is going to have kinetic energy because the bullet hits it and makes it start to move. So after the bullet hits the pendulum, it's going to have speed, it's going to have velocity. So it's going to have kinetic energy. It doesn't have any potential because it's as low as we care about it when the bullet hits it. And then at the end, when it makes its maximum swing height, it's going to have all potential energy because at the maximum height, it's not going to be moving anymore, so no kinetic energy. And there's no friction involved in a pendulum, so we don't have to worry about that. So this is our conservation of energy equation that we would be using. And you'll notice that 1/2 mv squared is going to be on the left, and mgh is going to be on the right, and the m's cancel. But ultimately, as I go down here, you'll notice that while I have g as 9.8, h is what I'm looking for, so I understand I don't know that. On this left side of the equation, I don't know how fast the pendulum was moving after the bullet hit that. And when it comes to a collision, energy can't do collisions, especially inelastic collisions. We need momentum for that. So I'm going to end this problem with energy, but the problem is I don't know what the velocity is. So that's where I'm going to need to use momentum. So what makes this a challenging problem is you've got to basically take two easier problems and put them together to make one more complicated problem. So the first thing we're going to take a look at is the conservation of momentum of the pendulum and the bullet when they hit each other. Initially, the bullet's going to have momentum because it's moving. The pendulum is sitting still, which is why this is crossed out. And later, the two are moving together. So momentum of the bullet prime, momentum of the pendulum prime, they'll both be there. When we expand that, momentum of the bullet times velocity of the bullet as it's fired out of the gun equals mass of the bullet times the velocity prime plus the momentum of the pendulum times velocity prime. These two velocities are the same because the bullet and pendulum stick together and move as one large object. We're trying to solve for how fast it's moving, this v prime, after the collision. That's the v that we need over here, how fast it's moving after they collide when the pendulum starts to swing. So we're trying to solve for this v prime. I factor it out because it's in both terms here, and then I can divide by the masses added up, which is why they end up over here in the denominator in this step. So on the left side, I have mass of bullet times velocity of the bullet. I just divided the two masses added together in the bottom, and that's going to give me my v prime. Mass of the bullet is 0.01 kilograms. Velocity of the bullet is 225 meters per second. The two masses added together, here they are, 0.01 kilograms times 0.3 kilograms. And I get a velocity of the pendulum after the bullet hits it of 7.26 meters per second. I already talked you through why we're using energy, because initially the pendulum has kinetic energy after the collision. Finally, it's going to have potential energy because it reaches the maximum height. 1/2 mv squared equals mgh. The m's cancel because they're on both sides. They'll leave me with 1/2 v squared equals gh. I just divide by the g, which is 9.8, in order to get h all by itself. And that gives me 1/2 v squared divided by g. Plugging in my numbers, 1/2 times the velocity of the two after they start their swing, which is 7.26 meters per second. Don't forget to square it. All divided by 9.8 meters per second squared. And I find out this pendulum must have swung to a height of 2.69 meters.